Continuing from the previous problem, so we had an inexact equation, we now made it exact, and now we're going to try and actually solve this exact equation, and it looks bad. All right, so trying to integrate with respect to y here, we have y terms, it's a bunch of integration by parts. But there is a nice trick you can do sometimes, and so I'll go ahead and show you that here. So we have this function f of x comma y equals c, and right, so Mars of x comma y plus Neptune of x comma y prime equals 0. So normally what we've done in the past is we went from Mars to f with an integral with respect to x. So we could also go from Neptune to f with an integral with respect to y, but that's going to be really difficult in this case because the n function looks pretty bad to integrate with respect to y. There's an alternative way to do this. So we could take Mars, we could integrate up to f of x comma y, which doesn't look so bad. We can integrate dx. And then that we have that, we can actually differentiate down with whatever result we get with partial y to get back to n and check to see if we're missing anything. Let's go ahead and do that. All right, so let's start with the easier one. So we should have f of x comma y should be the indefinite integral of Mars of x comma y dx, which is equal to indefinite integral of 2xy cubed e to the y. 2xy cubed e to the y dx. That's not a very difficult integral at all here. So the 2x will turn into x squared, and then we have y cubed e to the y. And then, right, we do need this function h of y in case anything's there. Now the next thing is we should have n of x comma y is equal to partial f partial y, and we can compute that fairly easily. So we're going to use the f from here. So we're going to have partial y applied to x squared y cubed e to the y plus h of y. All right, so if we do that, we have, let's see, 3x squared, well, okay, so this x squared here is kind of like a constant, so I'm going to have x squared. And I've got the y cubed e to the y, that's a product rule. So the y cubed will turn to 3y squared e to the y. Then the other half of the product rule, I need, right, the y cubed will stay the same, and I'll take the derivative of e to the y, and that is just e to the y, so that's not that bad. And then I've got this h of y, so I also need plus h prime of y. I'm not sure what h is, so I'm just going to have to write h prime of y. And I also forgot here, write the parenthesis for the x's. So let me just write that out now. So I have 3x squared y squared e to the y plus x squared y cubed e to the y plus h prime of y. So this was one way to get n, the Neptune of x comma y, but n is also, I can get directly from the ordinary differential equation. So that also has to equal, from the ODE, we have n is equal to 3x squared y squared e to the y. Right, that's the first term. Then I have an e to the y times x squared y cubed. So x squared y cubed, excuse me. And then I have a plus e to the y. And so the first term matches, the second term matches, and I have this h prime of y and e to the y. That's the only thing left I have to match. So I have h prime of y equals e to the y. So then h of y is just e to the y, right? The integral of e to the y is e to the y with respect to y. And so f of x comma y, if I go back to the f I found up here, it's x squared y cubed e to the y plus h of y, which is e to the y. So apparently, if we take the derivative of this thing with respect to y, we would end up with the n. And so, right, it's a lot easier to take the derivative than to integrate, right? If we had to integrate Neptune of x comma y with respect to y, that would have been a integration by parts. Looks like there's two of them. It would have been pretty terrible. But with this trick, you can also go in a slightly different direction. You can integrate through one path that's a little easier, and you can differentiate to get back to either Mars or Neptune. And then based on that, you can solve for either the h prime of y or the g prime of x to get your matching terms.